Thank you.
Where do I start? Well, 40 years ago, I was a very young lecturer at a teacher training college. Bill was a little older than I was at the University of Leicester and published a book, H.E. Armstrong and the Teaching of Science. A marvellous book for me beginning as a lecturer in science education. I particularly liked Bill's introduction as he painted a vivid picture of Henry Armstrong, and I thought, here's a man to watch in future years when he deals with famous chemists and famous scientists. And indeed, I'll mention but two of his important books. One is The History and Life of the chemist Justus Liebig, and the other, the chemist William Crooks. Two very famous chemists in the 19th century scene. There's a book still remaining to be written, and I keep on urging Bill to apply his skill to Robert Bunsen. So one day we'll get an account of the famous chemist who invented the Bunsen burner. Bill has had a most distinguished career in the history of chemistry. He was director of the Victoria Studies Centre at the University of Leicester for many years, editor of the Science and Chemistry History journal Ambex for about 20 years, and chairman of the sister society, the Society for the Study of the History of Alchemy and Chemistry, for between 1993 and 2006. He has been awarded several prizes for his scholarship, notably the American Chemical Society's Prize for the History of Chemistry in 1995, and the RSC's Historical Group's Prize, the Wheeler Award, in 2009. But I want to go back to Bill's writing. There are a number of people who write on the history of chemistry whose papers and books are soporific. If ever I can't sleep, I know which books to go to, take off the shelf, go to bed, cup of cocoa, read a chapter, and off I go. And if you give a large enough donation to charity, I'll name names. It's not the case with Bill. When he starts, or when I start his books, you can't put them down. Like a small child with a jar of sweets, you read and read and read and enjoy and enjoy and enjoy. His books are available at Amazon. I can recommend them. But I want to share a secret with you. In the history of chemistry, I don't think any author has made me laugh out loud and caused me to put down the book and recover from laughter. But Bill did. And the book was The Case of the Poisonous Socks. I shan't tell you where the page occurred that caused such merriment. He might not. If he has any wisdom, he won't, and encourage you to go to the back and, dare I say, go and purchase your personal copies. So, can I welcome you, Bill, to give our talk, The Case of the Poisonous Socks. Stories from the history of chemistry. Thank you.
Thank you, Alan, for that very big build-up. What you see on the screen, ladies and gentlemen, good evening, by the way, is a pile of old socks. And I regret to say that I'm actually appear to be wearing one of the samples. In fact, they are old socks. They were made by Nathaniel Cora, the big hosiery firm in my former teaching town of Leicester, for the 1862 exhibition held down at South Kensington. And they fortunately have been preserved in the Leicestershire Museum in their hosiery connection. Now, there is a story that I can tell behind this, which introduces, of course, William Crooks, here seen as quite a young man with one of his friends, John Spiller. And they were both at the Royal College of Chemistry in Oxford Street, where there indeed is a Royal Society of Chemistry plaque, if you can get near it, because it's a very busy bus stop just adjacent to it. He worked under August Wilhelm Hoffmann in the Royal College of Chemistry for about 5 or 6 years, and then went out to get himself employment. But one of his great interests while he was a student and an assistant of Hoffmann's was photographic chemistry. And if you think about it, early chemistry, early photography, I should say, was very much a part of chemistry. And indeed, you had to be something of a chemist, perhaps plus an optician, if you were going to master this new art of photography. Well, Crooks left in about 1855, went to Oxford and then to Chester, where he taught for a wee while, and then he got involved in editing photographic journals, 2 of which still survive to this day. And out of this, there came his idea to create his own weekly chemistry journal, the Chemical News. Unfortunately, it's no longer with us. The firm went bankrupt after Crooks's death, and the last issue appeared in 1932. But it is a marvellous organ of communication from 1859 until 1932, and it, of course, gave Lockyer the idea of a weekly Nature magazine some 10 years later. In 1861, Crooks discovered a new element, thallium, using the tool of spectroscopy that Robert Bunsen and Kirchhoff had devised in 1859. So this gave him some fame for a brief while. It got him a fellowship of the Royal Society, and then his career seemed to plummet. Nothing much happened. So he was on the lookout continually, I think, in the 1860s for some way of displaying his expertise, if you like, at chemistry. And one of the chances came in 1868 when the Times reported that a doctor in the City of London had gone to the local magistrate and complained that there were some dangerous coloured socks in circulation. And that these were giving rise to skin diseases or eruptions of skin on the leg and feet. And indeed, in one case, the surgeon, general practitioner, had to literally cut the boots off a gentleman wearing coloured socks because his feet had greatly swollen. So this gave rise to a little controversy, the usual sort of thing in the Times, lots and lots of correspondence that the editor was willing to publish. And along pops up Crooks and says, these aren't really dangerous, it's only that certain people perhaps are susceptible, it's due to sweaty feet, basically, which are interacting with these new coloured dyestuffs, the synthetic dyestuffs that my former teacher, A.W. Hoffmann, has encouraged from coal tar, aniline products, etc. So Crooks offers, if people will send him samples of these coloured socks, I will try and identify it, and identify the aniline dye, the culprit, and perhaps we can take it from there. In fact, he wasn't really an organic chemist at all. He'd been at Hoffmann's feet, but it wasn't his main interest. He's really an inorganic chemist. And although he translated books on dyestuffs from German, Crooks really wasn't a great expertise in dyes making and dyestuffs, so you won't be too surprised that he really didn't succeed in identifying what the particular poisonous dyestuff was. But it does illustrate, perhaps, something which you're all familiar with, I'm sure, that chemistry does have two sides, that there is a risk factor in the introduction of new chemical materials, which one has to take into account. As for Crooks, of course, from 1868 onwards, he was investigating the atomic weight or the atomic mass of thallium, which was something you had to do if you discovered a new element. You had to determine its atomic weight. And he spent over 10 years doing it. Absolutely meticulous, careful craftsmanship work. Amongst other things, trying to determine weights in vacua. In other words, at reduced pressure. And this led him into all sorts of anomalies, strange occurrences, which led him on to a little device that I hope you have seen called the radiometer, which you have what looks like an electric light bulb on a mount, and there are sitting on a darning pin are these veins, blackened and silvered alternatively, and it whizzes round in a marvellous fashion, mesmerising fashion, as the sunlight catches it, or even if you bring the warmth of your hand towards it. What on earth is going on in such an instrument? No one knew, no one could comprehend how to explain why these windmills went round and round in such a whirly fashion. But it led Crooks to a major investigation, which, to cut a very long, complicated story short, led him into cathode ray work, and ultimately, of course, in 1897, J.J. Thomson identifies the first subatomic particle as the cathode ray. So Crooks' work was extremely important. The technology of vacuum pumps and so on, work on cathode rays, and as you can guess from here, in the late 1890s, he gets involved in radioactivity as well, and he wears samples of radium in his pocket and does various tricks with them. And this is a rather nice caricature or drawing of him holding up a radium sample. By the way, that radiometer, I said it looks like an electric light bulb. The whole point is that it leads to the technology of the electric light bulb. Edison uses the vacuum technology that Crooks had introduced. Well, why am I interested in the history of chemistry? What makes it of interest? Here's someone you perhaps have not heard of at all, a German chemist by the name of Hermann Koppe. Though he's known to historians of chemistry because he was really the first person to write a masterful history of chemistry in German. Of course, it's never been translated, in the 1840s. He was a colleague of Liebig's at the University of Gießen. His own work, his own research, is in the area of what we would call physical chemistry. Today, it doesn't sound very enterprising or interesting. Colligative properties, how do boiling points and melting points and solubilities vary as you change the composition of compounds. But in the 1900s, it was still thought to be a very exciting. The future of chemistry lay in trying to relate composition to these physical properties. But above all, he was an historian of chemistry. And I rather like this quotation from the introduction to one of his later works on the history of chemistry. The alchemists of past centuries tried hard to make an elixir of life. Such efforts were in vain. It is not in our power to obtain the experiences and the views of the future by prolonging our lives forward in this direction. However, it is well possible in a certain sense to prolong our lives backwards by acquiring the experiences of those who existed before us, by learning to know their views, as well as if we were their contemporaries. The means of doing this is also an elixir of life. Now, I don't know about you, I rather like that. I suppose it's true of any kind of history, but it particularly applies to chemistry, I think. We can enjoy vicariously the future of chemistry through its past. Why was I interested in chemistry? Why did I first turn to be a chemist? Well, I blame this chap called Johannes Becher in the 17th century. Now, Becher, if he's remembered at all, is remembered notoriously because he invented the concept of phlogiston, the idea that a combustible, a burning substance actually contains a fatty earth which evaporates. And indeed it does. If you burn a matchstick, you can see the phlogiston coming out from the matchstick. So it wasn't a silly idea, but it meant chemistry remained in a kind of strange rut until, of course, Lavoisier, at the end of the 18th century, turned it all upside down, literally upside down, with the concept of the gas oxygen as causing the combustion. But Becker was a kind of roving alchemist, which sounds as though he was after that elixir or the means of turning lead and base metals into gold. But during the last 20 years, there's been quite a revolution in our understanding of alchemy. And by the way, there's a rather intriguing little exhibition down at the Science Museum if you're interested in alchemy. We now realize that chemists in the 16th and 17th centuries had to earn money somehow, and the way you did it was to gain a patron. Queen Elizabeth, for example, employed John Dee as her wizard, if you like. And all over Europe, all of those little kingdoms and principalities and dukedoms and so on were on the lookout for talented people who could advise them on how to improve the economics of their little kingdom, how they could build up their implements of warfare and so on. So there was a lot of employment for the alchemists, the chemist of the 16th and 17th century. And Becker was one of these, wandering around Europe, gaining employment in the different courts. But in 1660, he advertised what he called a portable laboratory, one which you could carry around with you. And it's rather an interesting sort of thing, because you can, it's a bolt-on. You can take it to bits, reassemble it in different ways, and you could use it not just merely as a furnace, but perhaps as a distillation device. And along with it, there was a bill of sale with all of these bits and pieces that you could buy. And people sometimes ask, when did chemists first wear a white coat or a brown overall? Well, Becker was certainly up to that. This awful looking thing here apparently is an overall, number 63. I don't quite know what to describe it as. Or again, nowadays you have to wear safety glasses if you're in the laboratory. Well, he doesn't have spectacles, but he does have this sort of piece of Victoriana which you hold up if you're at the furnace to protect your eyes, or if it's decrypitation, that lovely word which I think has lapsed from our vocabulary. If the thing's spitting, you hold this up to guard your eyesight and so on. Well, what he's really invented, of course, is the chemistry set. Becker's portable laboratory was quickly taken up by English public lecturers, and by the end of the 18th century you could buy these lovely little wooden chemistry sets which doctors bought to take to patients' bedsides, because urine was thought to be something which gave a hint of what was going on inside the body, disease and so on. And geologists and early mineral prospectors, particularly in Germany and Sweden, bought these sets. And by the early 19th century, English, British instrument makers were selling these kits, and they suddenly realized, well, children will surely be interested in these. The new middle-class parents would perhaps like to buy kits like this. So the chemistry set, not quite in the form, this form here, was certainly a 19th century product. But in the 20th century, just after the First World War, William Fröhlich in Switzerland, after the First World War, schools were ill-equipped or they'd been destroyed. Fröhlich had the idea as a science teacher in a secondary school of kitting out a little laboratory as a kind of portable laboratory, and he joined up with educational suppliers of textbooks and so on, and they go into cardboard boxes, and the chemistry set as we know it is invented and in circulation from the 1920s onwards. Now that's where I first started chemistry, and I'm sure my generation and the generation before that, that was what captured your imagination and your enthusiasm for this scientific discipline. And I might add, I think a lot of young children actually knew quite a lot of chemistry before they went up to secondary school, grammar school in most cases. Alas, of course, the chemistry set now, which you buy, is a pale imitation of those sorts of things there, where you might find benzene in the cardboard box, ether, certain dangerous substances, but not any longer. The risks are too great. There is recently a German history of the chemistry set, and the gentleman who wrote that book did look at the legal side and investigated and could find only one case in Austria in the early 30s, I think, in which a manufacturer was taken to court. A young toddler had taken some nickel crystals out of her older brother's chemistry set and, of course, stuffed it in the mouth. I forget whether the child died or not, but the parents sued. And thereafter, the manufacturers took great care in not necessarily taking out the benzene and the dangerous stuffs, but putting very prominent warnings inside the chemistry sets. Let me be didactic for just a moment. Introduce you to Frederick Guthrie, who taught physics to H.G. Wells, a splendidly bearded character. He had been a chemist, but he then went out to Mauritius, of all places, to teach in that former French colony, and found that there wasn't much chemistry to be done over there, but there was a lot of physics that needed teaching. So he transmutes into a physicist, and when he comes back to the British Isles, he ends up in South Kensington as Professor of Physics, along with Huxley and Franklin and other very important teachers. And H.G. Wells was one of his pupils. But H.G. Wells detested him. If you read H.G. Wells's autobiography, which is a very interesting book, he says some very nasty and unpleasant things about dear old Guthrie. And the real reason he doesn't like Guthrie is that Guthrie makes him make apparatus. All the students at the Royal College of Chemistry and Physics had to make their own instruments, which, if you think about it, is actually a very good idea. If you're going out to be a school teacher, and most of the students were, and the schools were not equipped with physical apparatus, it's rather nice to be able to wheel out a Wheatstone bridge or two and some optical instruments to teach your kids by demonstrations. And Guthrie, in fact, was a very important influence on physics teaching in America and Japan, and not just in this country. But he wrote books for children, and again, I just give you a quotation. I like this first book of knowledge, in which he says, "I want boys and girls, and so by and by everybody, to know about stuffs and things. Therefore, in this book, I've striven to make clear what stuffs are and how things are made from them. So I take such a house, as most of us live in, and show first of what stuffs and how its parts are made." Now, I like using that word stuff, because that's really what chemistry is about. It's about stuffs, how they interact, what stuffs you can get from other stuffs, and so on. And if you're interested in teaching, of course, what he's doing here is the object lesson. In this case, he's taking a house and taking it to bits and analysing what all the various stuffs are that go up to make a home. So continuing a bit didactically and painting a very big, broad picture, what we do in science, and particularly we do in chemistry, is what John Pickstone describes in one of his books as, first of all, we do natural history. We have to name the stuffs, we have to differentiate the stuffs, we need to classify the stuffs. And this involves you in all sorts of techniques, heating, subliming, filtering, and so on. And then there's the process of analysis, which is also involved. Sorting again into perhaps larger groups like acids, bases, salts, various other kinds of organic groups like paraffins and so on. And then, particularly in the 19th century, of course, there comes synthesis, in which we go beyond the analysis, or we use synthesis in order to understand our analyses, and go even further, as in organic chemistry, which initially simply literally meant the chemistry of stuffs that you could extract from vegetables, plants, and animals, to going on to synthesizing new materials that don't exist in real nature at all. We make new stuffs. That's synthesis. And then fourthly, is this process of making useful stuffs, stuffs that you can sell and make money from, or apply in military situations and so on. Now, I don't want you to get the impression that these are sequential activities of science or of chemists. These things were going on all the time. And to go back to Becher, for example, he is involved in his own scientific mentality, or chemical mentality, with phlogiston and so on, in doing useful things for his employers. Now, one of the things I'd like to draw to your attention is symbols. But one of the problems, I think, of the layman, the layperson, is that chemistry does seem to be written in a strange language of hieroglyphics. But then if you were living in the 17th or 18th century, you would actually be faced by symbols like this, which look even stranger, I think you will agree, to those that chemists use now. These were symbols that alchemists and pharmacists had developed, which not only stand for certain stuffs, but actually also in many cases stand for what you should do to a stuff, like dissolve it, etc. And then at the beginning of the 19th century, up in Manchester, John Dalton develops a new notation, because he has this idea of an atomic theory of matter, which Lavoisier, 20 years before him, had rejected completely. Lavoisier had, however, defined the chemical element in the way in which we would understand it today. Operationally, if you can't analyze a material and break it down into something smaller or lower in weight, that is, or in mass, then let it be called an element. And in that way, he'd got a list of some 50 elements. And Dalton said, well, let's suppose that these elements are made of atoms. And the reason why one element stuff differs from another elementary stuff is that it has different mass, it has a different weight. So you've now got 50 different atoms, as well as 50 different elements. And he symbolizes these in this rather odd mixture of the round atom with a signal inside, which sometimes is the alphabetical symbol. But notice the atomic weights. If you choose hydrogen, the lightest known stuff there is, as your baseline, standardization, then, for example, oxygen, to simplify, is 16 times heavier. Doesn't say that there, but let's say it's 16 times heavier, etc. And notice they're all whole numbers. So along comes a London doctor, William Prout, in 1816, and he says, hold on, God surely would not have devised, created a world in which there were 50 different stuffs and 50 different atoms. Surely God, in his infinite wisdom, would have made things simpler. And the reason why atomic weights are whole numbers is surely because oxygen, 16, is 16 bits of hydrogen glued together somehow. This is called Prout's hypothesis, or becomes known as Prout's hypothesis. And it is of major significance in the 19th century. It runs right through the century, creating a lot of analytical work. Because could you disprove it? Well, take chlorine, it's 35.5. Is that really 35, or is it really 36, or is it nothing at all? Is it because, as Prout then said, it's half a hydrogen, which is the basic stuff, the Urstoff, the protohyli, as he calls it from the Greek, out of which all the stuffs of the world are made. So as you might imagine, this led to an enormous controversy which runs right through the century. And physicists are still at it, of course. They've got far too many bits of atom, far too many. And one of the reasons you've got a Hadron Collider costing millions of pounds is that they're desperately trying to find some simple solution to the huge number of oddments and bits of stuff that they have got. Now, the greatest chemist at the beginning of the 19th century was a Swede by the name of Jakob Berzelius. He didn't agree with Prout's hypothesis at all, but he is the man who gives us the modern chemical symbol. In 1814, it's not a suitable page to illustrate, but he simply says the chemical signs ought to be letters for the greater facility of writing. Of course, Dalton's, you've got to have this circle as well, which is a bit of a nuisance if you are a printer. I should take, therefore, for a chemical sign the initial letter of the Latin name of each elementary substance. But because we have some elements which have the same initial, I'll have to distinguish it in various following manner. So iron is Fe, but F is fluorine, for example. That sort of thing is what he means. But now, think about it. In the 1830s, there was a great controversy at the British Association for the Advancement of Science on which system to use. Should you use Dalton's circles with letters in them, or should you use Berzelius' system of FeO, etc.? At the very beginning, of course, if you want to say iron oxide, you say Fe plus O. But gradually, chemists squeeze the two things together, so you have Fe and O adjacent, or in water, H2O, etc., written as a single block. And the mathematicians started to complain. This is an algebraic way of expressing things. People are going to get terribly confused if chemists write things one way but mean something entirely different. So there's a little row over that, but the chemists had the upper hand. They said symbols can mean what we want them to mean, and that was it. But I must mention that Arthur Schuster, who was an Anglo-German physicist, in 1903 at one of the British Association meetings, gave a joke paper. And chemists and physicists do this sometimes and get away with it. He gave a joke paper, and it was the algebraic way of interpreting chemical symbols. Now, I think you can bear with me that hydrogen plus chlorine gives you an irritating gas called hydrogen chloride, which you can put in water and get hydrochloric acid from. And the actual equation is, as you see, HH plus CCl equals 2HCl, or if you prefer, H2 plus Cl2 is 2HCl. Now, if you treat that as an equation, take 2HCl from both sides, as my algebra teacher used to say, and you get H2 plus Cl2 minus 2HCl equals 0. And if you drag back into your memories quadratic equations, a squared, a minus b all squared is a squared minus 2ab plus b squared. So treat it like that, and you transform it into h minus cl all squared is 0. Take the square root, and h becomes Cl. In other words, you've proved that hydrogen equals chlorine. Strictly speaking, it should be plus or minus chlorine. So you've got two possible solutions, but Prout's hypothesis, if you like. But this is all a complete joke. But the formulae do move on. Alexander Crumb Brown, who was a professor of chemistry up in Edinburgh, this is a cartoon of him. I'm not sure how. One can't see, actually, that on the blackboard, the reason these poor students in front are gasping for breath is that the equation written on the board is iron sulfide plus this hydrogen chloride again gives H2S, which is bad eggs, the poisonous gas hydrogen sulfide. So the students are left gasping. But Crumb Brown developed he went back to Dalton, essentially, and for organic chemistry, begins to give you these formulae, these strings, which you'll notice have lines, or bonds, as Edward Franklin was to call them. So the chemical bond is coming into display here in the early 1860s. Which brings me to Hoffmann, whom I have mentioned, the teacher, the pupil of Liebig's, who came to England and set up this Royal College of Chemistry. He stayed here 20 years, but in 1865 the call came to go back to Germany. He became professor of chemistry in Berlin, where he built up the great German dyed stuffs industry. But in his farewell lecture, given in the Royal Institution just across the road here, he introduced molecular models. Molecular models. He took a croquet set, or perhaps they were billiard balls, bored holes in them, and strung them up on these, I forgot what they call them, the tripods, to display what chemical formulae looked like according to the Crumb-Brown rule. So molecular models come in, and pretty quickly instrument makers are making not chemistry sets, but molecular model sets. They were called glyptic models, to do with art, I suppose, glyptic. And what you see, the billiard balls with holes in, and the chemists can make these models and demonstrate them to students to demonstrate the composition of organic compounds. This was the absolute last straw for Sir Benjamin Collins Brodie, Professor of Chemistry at Oxford, who was a pupil of Liebig's, but who had decided that atoms didn't exist. The atomic theory was utter metaphysics. It was something that chemists must at all hands strip away from their minds. They must not think in terms of atoms. And so determined was he to eradicate the idea of the atom that he had to get rid of Dalton and Betzelis's chemical signs, chemical symbols. Because if I write Fe down, that automatically means an atom of iron. Can't have the idea of atom. So you've got to think of some other way of developing a chemical notation. And up he came with the calculus of chemical operations in 1867, thereabouts. And he uses Greek letters, not Latin letters, which is immediately annoying to chemists because it means you've got to learn another alphabet. I won't even attempt to go through this, but you can see these alphas and xis and perhaps some other things here. The chemists didn't know what to make of this. There was a famous lecture in the Old Chemical Society in which literally hundreds of chemists attended. They couldn't make head or tail of it because it actually is Boolean algebra, and that really foxed chemists. They didn't know any mathematics at this stage of the game. Nowadays, of course, you are expected to have some quite advanced mathematics to be a decent chemist. But what the chemists did seize upon was that the symbols seemed to fall into three sets. There were symbols like just an alpha. There were symbols like an alpha xi. And there were symbols like xi squared. Now, alpha chi squared was chlorine, but it seemed to have alpha and chi. And alpha xi squared was water. So chlorine and water definitely was a compound. Was chlorine a compound? So what the chemist seized upon was the idea, again, of this Proutian idea, that perhaps all those elementary stuffs are really compounded, and we're back to Prout's hypothesis. And it was just about the time that spectroscopy and astrophysics were emerging, and you've got all those strange lines that are being photographed from stars and from our sun. And again, it seemed to be that you've got harmonies and similarities in the lines of composition of your spectra. So Prout's hypothesis was up for grabs again. Let me switch tack and go back to someone whose name has been mentioned by me, Justus Liebig. Here he is outside his famous laboratory in Gießen. And please, if you are in Germany, do go to this little university town of Gießen, quite magical, Liebig's Museum. Liebig's Museum is in fact the laboratory that he built in 1840, and here he is in a daguerreotype standing outside. Here he is, much older man. He left Gießen in 1852 and went to Munich because he fed up with teaching, basically. But at Gießen, where he'd spent most of his career, he became a very great teacher indeed. People from all over the world flocked to his great teaching laboratory and research laboratory. And this laboratory now looks almost familiar, doesn't it? We've even got a fume cupboard at last here, so that you don't have to go outside to do dangerous, smelly reactions. But no one's wearing a lab coat. Poor old Becker's sales obviously hadn't been all that efficient. But they are wearing hats still because there are a lot of carbon charcoal floating around the lab, I imagine. This gentleman here is actually Hoffmann, Liebig's favourite pupil, the one who was to build this Royal College of Chemistry in Oxford Street, as I have mentioned. In fact, it was opened in 1846, and there is a report in a German newspaper of the opening of the Royal College of Chemistry. It's very interesting, and I have put a translation in my book. And the reporter was a pupil of Liebig's, German, by the name of Diefenbach, who was a naughty student. He got involved in politics in the revolution that failed in the 1833, and he was exiled. He was kicked out of Germany, went to Switzerland, and came to Britain, where he set himself up as a reporter, a science reporter for The Lancet. And by various ways and means, he got chosen to be the ship's doctor and naturalist and geologist for an expedition to New Zealand from 1839 to 1842. So although you've perhaps never heard of him, if you go to New Zealand, you'll find that Diefenbach's name is still revered. There are mountains named after him and so on. And this, as far as I can tell, is the only known picture by the ship's artist. This is Diefenbach here, and he's been serenaded, if you like, by a group of Maori chieftains and his daughters or wives. He wrote a very interesting account of the opening, in which he more or less puts Britain down to size and says, you know, it's not going to be much good, or it hasn't so far been very good at chemistry. But now we've built this institution under Hoffmann, great things can be expected of British chemistry. Now, Liebig's writings, to my mind, are of enormous significance for the history of chemistry. Just consider that his first book in 1840 was called Agricultural Chemistry. And his books were translated into every important language, including, of course, English, simultaneous translation. The importance of the agricultural chemistry was that he had devised artificial fertilizers. Why go through all this business, thousands of years of rotation, when you could put back what you've taken out as food by putting back some chemical materials? And this gives rise, of course, to the superphosphate industry. And to do that, you've got to have sulfuric acid. So building on the back of fertilizers, you start to have the heavy feedstock industries of making acids of various kinds. I'll leave it at that, but of course those fertilizers didn't necessarily work very efficiently. I won't go back. Animal chemistry, 2 years later, brings in biochemistry, because Liebig, even in the first edition, does what one would call paper chemistry. Those formulae that I showed you, you can write them down as an equation. We know what we eat, starch and protein. We know what comes out in our excretions and so on, because you can analyze them, and that balances. Or you can make it balance anyway. But then you do your organic chemistry, and you know what's going on inside as well, or what the organic materials are, and you can invent equations This is what biochemists, even to this day, essentially do. And then in 1843, a great work of popularization, one of the greatest works in the 19th century, the chemical letters, popular letters in a newspaper. And then the chemistry of food, in which he gets involved in nutrition and develops, in fact, an industry out of that. And last but by no means least, in view of this geological lecture that's coming up, the utilisation of sewage in 1865, actually written to the Lord Mayor of London. That's, of course, the City of London, but I think Boris would perhaps be interested in it, because the sewage was going to go out to the Maplin Sands, where I suppose the airport is supposed to be built. But recycling of sewage, very important idea, and it's very influential. If you go to Melbourne, you find these enormous tracts of land outside the city where you have a huge sewage farm. The extract of meat, of course, is very much associated with Liebig. What about all those waste carcasses in Uruguay in South America, those vast ranches where the cattle are reared for their leather or for the oil that can be used in lighting? But the meat is just rotting on the ground, which must have been a terrible sight, I think, in the midday sun in Uruguay. But Liebig had this idea of plastic foods and muscle foods, and he thought the juices of muscle, the juices of flesh, were very, very important, and he used them, little soups made up of these extracts. And then someone had the idea of setting up a company, and they invited Liebig to be sort of chairman, lend his name to a commercial product. And if you go on the continent to this day, you can buy jars of the extract of meat. This is an example where the extract is added to wine, so you get a double bit of energy out of this. And there's great warfare going on between the rival companies that get developed. This, I think, is a shot outside Waterloo Station in the early 1900s, because we've now got OXO, which is the solid form of the extract of meat. And we've still got it. We still use it. And the great rival was Bovril. And I noticed in the Captain Scott exhibition, which I visited this morning at the Natural History Museum, that Bovril was the stuff that Scott and his company took on the abortive visit to the South Pole. And Liebig also developed the first formula, which what the Americans still call it, milk formula, for mothers who are unable to suckle their young, or in a society which was gradually getting rid of other women feeding other people's children. The best food for infants, savoury and more. And other companies, Mellon, these are apothecaries who take this business up. And of course in Switzerland, Henry Nestle, Nestles, develops this milk formula as well, and they diversify these companies into things like chocolate, of course, and into soup making of various kinds. So Liebig is very important for generating the chemistry of food and the huge food industry that has developed out of it. I think I read a statistic somewhere, but by the 1930s, more chemists were involved in food chemistry, food making, than in any other industrial process in the British Isles, and that may even still be true. How are we doing? Where does the money come for paying for research? Well, governments, military, universities, etc. But sometimes philanthropists come along and offer money. And you have to be very careful because there may be strings attached. And this gentleman here was in fact an Englishman, but he spent his entire career in America as a sweet manufacturer. And he became a millionaire, if not a billionaire. And reaching his late 80s, early 90s, I think, he decides, I have no family, I must give all this money away. He gives it to all sorts of worthy charities, but he offers a large sum of money to the Smithsonian Institution in Washington. And he also offers money to the Royal Institution. And just as today, the Royal Institution was impoverished and desperate for money. The trouble was that Hodgkins seemed, I suppose, a bit elderly, and he had rather strange ideas. He'd read an awful lot of Herbert Spencer, and he thought civilization was going to the dogs. And it had something to do with impure air, and air was the Holy Spirit. He was a very deeply religious man. So if you see things like that, you wonder if the man is entirely sane. You have cause to wonder, should you really take money from someone whose ideas are a bit odd? But the Royal Institution did take the money because James Dewar, the chemist, who was the director of the institution, was involved in the liquefaction of air, which is a very costly business, refrigeration plants. Indeed, the Faraday Museum area of the Royal Institution then looked more like a ship's engine room because of all the pumps and various things. So Dewar took the money. Now, as the chairman hinted, there is something more to this story, but I will in fact leave it at that. Finally, ladies and gentlemen, I was going to say something about what I've called lost chemists. People who go into chemistry and then, for various reasons, get out of it again. I have three here. In fact, someone yesterday reminded me of another one. John Christie, the founder of the Glyndebourne Opera House. If you read Douglas Hume's autobiography, you'll find that he was a pupil at Eton just after the First World War, where Christie was a science master. And Lord Hume gives this nice anecdote how Christie would come to the first class in the morning, still in his dressing gown, and would tell the boys to turn to page so-and-so. And then Christie's butler would come in with his breakfast, and Christie would sit there eating his breakfast while the boys mugged up their notes. And then the butler would come back a quarter of an hour later and say, "Your bath is ready, sir." So that was the state of science teaching, or one aspect of it, at Eton in about 1919. But then, of course, come 1920 or 21, Christie inherits the Glyndebourne estate, marries an opera singer, and they build that marvellous facility down near Lewes. George du Maurier, better known as an artist now, and indeed an author of Trilby, and known as the father of the actor-manager and grandfather of the author, whose name I forget, but Daphne du Maurier, the author of Rebecca, made into a famous film. But he began life as a chemist. He trained actually at University College London in the Birkbeck Laboratory, which was still up and running when I began chemistry in 1956 at UC. And that looks much more like a modern laboratory, perhaps. He did work for a few years as a consultant chemist, du Maurier did, but then he was asked by a syndicate to investigate the metallurgical properties of a property that the syndicate had purchased in Cornwall. Du Maurier did the necessary analysis and said the whole thing's a load of poppycock, you'll never make any money from this. The syndicate was very unhappy at the report, and that was the end of du Maurier's consultancy career. He decided instead to use his artistic talents and become a draftsman. Doing cartoons like this in Punch, joke about the Victorian doctor, who says, "Oh, how good of you to come, doctor," says the lady in the chair. "I didn't expect you this morning." "No," says doctor, "I was called to your opposite neighbour, poor Mrs. Brown, and thought I might as well kill two birds with one stone." Typical Punch cartoon of the 19th century. Which reminds me that a lot of chemists are extremely good with their drawing ability, and you had one, I think, at the last meeting, Andy Abbott from Leicester. I think I heard him say he paints every day, as well as doing green chemistry in the lab. But this is Mellor. My generation knew Mellor's textbooks, and you perhaps have heard of the enormous, 35 volumes of Mellor's Comprehensive Inorganic Chemistry. Encyclopedic. Mellor did it by hand, everything. It has no collaborator collaborators at all. But he was a ceramics chemist, and he had a dab hand at artistic work. This is Mellor here, and there's a nice little story he's telling against himself. He gets very angry with this gentleman here, who's pinched his seat while he's been eating in the restaurant car. I got time, Pauline. This is a nice story of Nickel, who was an organic chemist, trained with Hoffman, no less, lectureship at Bristol, and then a lectureship in Birmingham. But in 1894, when Tilden left Birmingham and came down to South Kensington here, Nickel thought that he would get the chair. He would be the natural replacement, but he wasn't, and Birmingham busted in Percy Franklin instead. So Nickel resigned. He gave up chemistry completely and led a life of Riley, building himself his own caravans and spending some 30 years traipsing round the Highlands of Scotland. I think it's marvellous. There was some money behind this. He had inherited some money. And finally, C.P. Snow, whom I only chose to mention because he was the first chemistry graduate at University of Leicester, or the old University College of Leicester. Here's the familiar picture of the elderly Snow, novelist, corridors of power man. There he is as a young man in the college play in the school grounds about 1926. You could just about make out his visage there. He was the first chemist at Leicester. He was a bright young man. He went into spectroscopy, got a scholarship to Christ College, Cambridge, and did some research, some serious research in spectroscopy. Things didn't work out terribly well, and he decided he preferred literature anyway, and he started writing novels. Above all, The Search, which is a very good science novel, about 1932, and that long sequence of novels about power and politics. And finally, since you've borne with me for so long, what I've tried to do is to show you something of the intellectual quality of chemistry. But I thought I'd end by a quotation from one of my great friends, David Knight, who's also written extensively about the history of chemistry, and notably on Humphrey Davy. He has this wonderful way with words, does David Knight, and he really captures, I think, what those of us who've done chemistry really feel about the essential power of chemistry. Chemistry is an empirical science, and the textures of stuffs get into the memory. You can't forget something once you've touched it. You remember the viscosity, mobility, and viscidity of different liquids, and the gritty, unctuous or glassy feel of solids, the indescribable but unforgettable smells of things, colours and their changes, the tastes of things tried voluntarily or accidentally through a mismanaged pipette, the bubblings, the test tubes becoming too hot to hold, sharp colour changes, sudden turbidities, precipitations. These are the stuff of chemistry. And I still remember dipping my hands in mercury. And it's the most strangest feel, because you bring your hand out, there's no liquid there at all. There's this strange feel as you put your hand in the mercury. Can't do that now, even. Thank you very much, ladies and gentlemen.
Thank you very much, Bill. I noticed in the last list you didn't mention the memories of things that go bang. And I have my own collection there. We've got time for 1 or 2 questions. There's going to be a roving microphone coming round. Could I ask the person who's asking the question to state who he or she is, and if they have an affiliation, what that is? So can we have some questions, please, to Bill? At the back there, please. Just wait until it arrives.
Thank you. Can you give us an idea of what the proportion of those who believed in the atomic theory and those who did not? What was it around at the beginning of the 1900s compared to the beginning of the 1800s?
Yeah, well, that of course is something. Sorry, I have to switch my microphone.
Well, come here, Bill.
I can do it from here. Sorry. That is something that is impossible to quantify, of course, but my own impression is that the vast majority wanted to continue to use the atomic theory because it was so useful heuristically. If you were teaching, it was a kind of foundation for the imagination of what is going on. Nevertheless, there are a number of quite significant 19th century chemists and physicists, like Mach, for example, who did continue to object, and they object right up until the time of Ostwald, about 1908 thereabouts, when through Brownian motion and Einstein's work on that, it becomes possible to say, well, definitely there are things hitting and bombarding. There is a molecular structure.
Thank you. Any more questions, please? Wait until the microphone comes. It's coming down. And could you tell us who you are, please?
Hello, my name's Alan Bodley. I'm retired. Just intrigued to understand why so many chemists in the 19th century were Germanic. Was there a reason for that?
Sorry, Alan, I come in.
Why were so many chemists of the 19th century of German origin?
Oh, gosh, yes, of course, yes. Well, it is a very interesting question. The answer, I suppose, is that the chemists move very fast in developing a teaching mechanism for chemistry. In Britain, if you think about chemistry in the 17th century, etc., you've kind of got individuals. You've got very few people that you can identify as a chemist in Britain. The same is true in the 18th century. It's only at the beginning of the 19th century that perhaps the population size increases, but there are no institutions in which you can learn it. You've got to more or less teach yourself until people like Liebig developed these teaching institutions. They're primarily teaching institutions. So you have to learn German. You go over and learn it physically at the feet of the teacher. And then after Great Britain does develop chemical institutions for primary teaching of chemistry, then they encourage students to do postgraduate, as we would nowadays say, go to Germany because that teacher taught me and they were jolly good. And so you get this idea right up until 1914 at least, Americans as well, not just people from this country going to German. And you had to read German right up to my generation. I suppose in the 1960s it finally stops, and American literature is overtaking that of the German literature, so you don't need to read German anymore.
Anybody else, please? Gentleman over there, wait until the microphone comes down, please. And you are?
I'm Mike Lilly, I'm retired.
Cool.
I just thought you might like, whether you knew a story about C.P. Snow from the University of Leicester, because I was there in the middle 50s when Louis Hunter was the head of department.
Yes.
And when we were working in those laboratories, in one of the undergraduate laboratories, there was some stains on the ceiling. Remember these? No? These stains were on the ceiling because C.P. Snow was held in some sort of, regard. He was a individual student who did things his own way, and this was the result of one of his chemical experiments. And even though he'd left ages, until they changed those laboratories, they're now part of the administration of the university there, they left those stains there until they changed their building ground. Thought you might like to know, if you didn't already know.
I have heard that story because it's one of those stories that circulates through the labs. Yes, he wasn't a dab hand at practical chemistry, and I think it was a Scrap reaction which just blew up. There's a
Is it true, Bill, that he was made in future to clamp an asbestos square over his reflux condenser so when the contents of the flask went upwards, they wouldn't hit the newly painted ceiling?
Probably, yes. I have a story about Louis Hunter, of course, because when I went up to Leicester, it was building for the first time a proper chemical laboratory. And Hunter, I remember, insisted that he have his own bathroom and shower. I suppose it's rather a good idea for a chemist there, but it reminds me also of Hoffmann, of course, when he built the University of Berlin Chemical Institute. He built himself a ballroom.
Can I just say that Louis Hunter, the new building was called the Pride of St. Louis, because he's Louis Hunter, and yes, we know all of that story. He really wanted things in style. Yes.
Yeah.
Thank you. We have a lady there halfway down the hall.
Thank you. My name's Sally Brearley. You were talking about William Crooks and these sort of strange invisible effects. Am I right in remembering he was a spiritualist?
Yes. One of the ways in which he did become famous, or should we say infamous, was that the radiometer that he had developed, he found that you brought your hand towards it, it rotated. And he wondered whether this also linked together with mediumistic powers in some sort of way. So he got involved in these physical apparitions and even photographed ghosts, if you like. But this developed into scandalous proportions, and it didn't really do Crooks much good until he got away from it, or perhaps he didn't privately he continued, but in public he sort of gave up his enthusiasm. And cathode rays, just simply made his fame and fortune, knighthood, presidency of the Royal Society and so on, everything you could wish for as a scientist.
And Bill's book on William Crooks is, I have to say, less than £20 and is a rattling good read, I can tell you that. And there's a lot about him dabbling in spiritualism in the book, so I can recommend it. Any more questions?
Very heavy book, I warn you.
Heavy in mass, but not in content. Well, I will conclude with, before we move to thanks, by just some of my recollections, because I was introduced to chemistry by the chemistry set of that period. And in Blackpool, where I lived, there was an enterprising pharmacist who used to sell all sorts of spares for chemical sets. And I can well remember going home with paper envelopes of iodine, of potassium permanganate, and all the rest. But he knew if a child went along asking for sulfur, potassium nitrate, and powdered carbon, what he had in mind, so the answer was no. However, if you sent your mother along, she could come back with bottles of sulfuric acid, globules of mercury, and indeed the potassium nitrate so required for the manufacture of gunpowder. Two lots of thanks for tonight. First of all, to the RSC and to Pauline at the back there for organising this lecture and this meeting. So let's show our appreciation to her. And then to our speaker. Now, I referred earlier on that the fact that in his book, he made me laugh out loud. But we've all been chuckling tonight, with stories from his history of chemistry. It's been a most delightful talk, Bill, and I thank you very much for giving your time to come and talk to us. So shall we now give him a round of applause to thank him for this.
Thank you very much.
You can now chat if you wish to Bill and others outside as we have a cup of coffee before we go on our way.